So from looking at your work, it seems we need a little bit more practice with the swinging bar type problem or the swinging whatever type problem. So I'm going to walk you through a problem. I'm going to delineate what the problem is, and then I'd like you to stop the video and then try it yourself, and then I'll walk you through the rest of the solution. If you remember from the moment of inertia sheet, there was a composite system that consisted of a hoop whose mass was m and whose radius was r, attached to a disk whose mass was 2m and a radius of 2r. And the system was pivoted at that center. Let's say that this system is what we have, and this system is held such that the ground is this way. Okay? So if I were to hold that system in place for a moment and then let it go, I think we would all understand that what would happen here, if I were to draw a line here representing where the center of mass of both the disk and the hoop are initially, that because this mass is less than this mass, and because this lever arm is greater than this lever arm, the torque on the disk is going to be greater than the torque that's generated here by the hoop. So there's going to be a net torque going clockwise here. So this is going to swing downwards and that's going to swing upwards. Now, at some time later, what we will see is the hoop would be here and the disk would be here. Now, it wouldn't stop there. It would be continuing through on its motion, but this would be the place where the hoop and disk combo would be moving fastest. So what our problem is then for this, I want to know this point on the end of the disk. How fast, I'm going to call point P. How fast is P moving when the disk is at its lowest point? And just while we do this as well, we'll pick a point Q and ask that same question about Q as well. And so that's what the problem is. So I want you to give this a whirl, and so stop the video, and then we'll come back here and I'll work this problem through with you. All right, so you've hopefully tried the problem. Let's go through a couple of things. First, there are two main solutions to this problem. The first solution is we are going to treat the disk and hoop separately. Okay? And we're going to do conservation of energy. Actually, there's probably a lot more than two solutions, but both of our solutions are going to use conservation of energy because doing this with torques would just not be a good time because of the calculus. Our second solution is going to be treat the body holistically. Right? Now, to some extent, we're going to treat these bodies holistically, like treat the hoop, the disk, or the whole system holistically, no matter what. So let's get started with this. So here's what we have. Here's our initial A, here's our final B. I'm going to make this the UG is equal to 0 line because it's a convenient place since both of the objects initially then will have 0 energy. So no matter which solution we're going for, the energy at A is going to be equal to 0. The energy B here, if we're talking about the first solution, finally, well, we can see that the hoop has gravitational potential energy because it's no longer at the UG is equal to 0 line. We can see the disk has gravitational potential energy because it's no longer at the UG is equal to 0 line. And both we're going to have rotational terms as well. So that's what that solution looks like. Now in this solution, EA is equal to 0. Now EB, if we're treating the whole thing holistically, I don't care about the disk or the hoop. What I care about is the center of mass of the system. Now we don't know where that is yet, so I'm just going to put an X somewhere where I believe the center of mass is, because it's going to skew towards the disk. Since the disk is more massive, we'll find that later, right? We're going to have just one term then for UG of the system, because all I'm going to care about is where that center of mass point is after this thing has swung. And that's the benefit of this. Also, there's going to be just one KER term, which is a lot simpler there. Now, this solution is going to require a little bit more setup. So let's start doing that setup now, no matter what. So I'm going to talk about moments of inertia because we know we're going to need them. I of the hoop here about this point. Well, I need the parallaxis theorem, so that's I com of the hoop plus mass of the hoop, and then the shifting factor for the hoop. And so that's going to be mr squared plus the mass of the hoop is m, the shifting factor is r squared, so that's 2mr squared. We've already actually done this problem. I'm kind of just walking you through this solution there from before. I of the disk is going to be I com of the disk plus mass of the disk, d of the disk squared, right? Because once again, the disk is not being rotated about its center of mass. And so that's going to be 1/2 mr squared, but the m of the disk is 2m, the r of the disk is 2r, there we go, quantity squared, plus the mass of the disk, because that's what I'm performing the parallaxis theorem on, 2m, and then the shifting factor. The shifting factor here happens to be the radius of the disk, so 2r quantity squared. So if we look here, 1/2 and 2, that's 1, 4, so that's 4mr squared, and then 2r is 4r squared times 2 plus 8mr squared, so that's 12mr squared. So we're going to need both of those for this solution. But if we're talking here, we're going to need I of the system. I of the system is just going to be I of the hoop plus I of the disk, and we've actually already done that problem, and that's 14mr squared. Okay? So just adding those two together. So there we go. That's our prep work. Let's get into actually doing these solutions, and I'll be referring back to this page as we go through. No matter what, I know EA is equal to EB. Because the work non-conservative is equal to 0, we have only gravity doing work here, and so that makes that nice and simple. So here we go. We know that this is 0. We know that this is UGH plus U is equal to, UGD plus KERH plus KE R of the disk. So there we go. 0 is equal to. So this is mgy, so the mass of the hoop is m, then I have g, and the y final of the hoop, when it's in position B, is up a positive r. So I'm going to put that in plus r. Now for the disk, we're going to have 2m, because that's the mass of the disk, g times what is the position of the center of mass of the disk at the position I care about. It's at negative 2r, because it's below the UG line, there we go, plus 1/2 I of the hoop, which we found out is 2mr squared, omega of the hoop squared, plus 1/2 12mr squared, omega the disk squared. And so let's stop and talk about that, because the disk hoop system is a rigid rotating system. That means that omega is going to be the same for all points on this and for all parts of this. So really, I'm just going to cross these out, because this is not omega the disk or omega the hoop, it's just omega. Now, by now you should have noticed that the problem is asking for the speed of points. But at no point here have I even addressed that. That is because our analysis does not deal with points. It deals with a holistic, rigid, rotating object. the point P and the point Q do not have potential energy. The reason why I'm able to talk about these points as having potential energy is because those are the potential energies of those whole objects holistically. Technically, there was an integral behind that. We just didn't show that, right? You couldn't do mgy for this because not all the mass of the disk is located at point P. But we said the center of mass of an object is where we can pretend all the mass is located for purposes of translational motion and in terms of energy. That's how I've been getting away with it, right? And so what we're going to do here is we're going to find omega, and once we know omega is the same for every point on this body. I can then talk about what's happening to individual points on the body. All right, so with that little sideline, now it's just a bunch of algebra. So let's see what we have here. I've got mgr, and I've got 4 mgr with a negative, so I'm going to bring that over to the other side. So that's a total of 3 mgr, okay? Here, I've got half of that and half of that, the omega squared. So that's going to be 1 mr squared, and this is 6 mr squared. So this is going to be 7 mr squared omega squared. And now I can just do the m's canceling, right? R's canceling. And then I've got 3g over 7r square root of quantity is equal to omega plus or minus, and I don't care about that because I'm looking for a speed. So that is the omega for every point on that object. So from there, if I want to know now about the translational motion of individual points on that object at moments in time, now I do omega r. So no matter whether I'm looking for VTQ or VTP, knowing omega is the first step in that problem. So for VTQ, that's going to be omega times RQ, right? Since omega is the same. So that is the square root of 3g over 7r. Okay, and RQ, if we look there, from the axis of rotation, that's 2r upwards. So times 2r, and I'm not even going to simplify. Actually, if I simplify that, just to make it a little bit nicer, I'm going to pull the 2 inside the radical, so that's a 4. So that just becomes 12 sevenths gr, because if I pull the r inside the radical, it's an r squared there, which cancels with one of the r's. So VTP then is omega rp, and so that's the square root of 3g over 7r times, and well, where is point P? Well, that's 2r and 2r, so that's 4r downwards from where I care about. Boom, let's pull that inside the radical to make that look a little bit neater as well. That becomes 16 inside the radical, 48 sevenths gr. And there we go. Those are our answers with that solution. Now, let's look at our second solution, right? So our second solution requires us to know something about where the location of that center of mass is after it has rotated downwards. So I'm going to do a center of mass problem. If I say this is 0, 0, and to the right is positive, that's an x-com there or an r-com, whatever it is that you want to, along this axis here I've drawn. We'll just call it x for the moment, even though it becomes a y. Actually, you know what? Never mind. We're going to make it r because it's kind of along a radial line no matter what. So this is going to be the sum of the mr's over the sum of the m's. And so I'm going to have a hoop term, so that's m times negative r, because it's going to the left there, plus 2m times 2r all over m plus 2m. So I've got up top, I've got 3mr over 3m. Oh, so good, it's just at r. I was kind of right about where its location is. It's just r that way. So how do I use that now? Look how simple this is. EA is equal to EB, because work non-conservative is 0. EA is still 0, so this becomes the potential energy of the system, right? So that's going to be the mass of the system, because I'm treating the whole thing like one object, so that's 3m g, and then it's where is the center of mass term, and that center of mass term is negative r below the UG is equal to 0 line, right there. Plus, 1/2, and then I of the system, which we found to be 14mr squared, and then omega squared. So let's move that over to the other side, and I've got 3mgr is equal to 7mr squared omega squared. Now, you may stop and say that's very familiar, and you'd be right, because that's exactly what we got right here after doing all of that work. Right? So the question is just kind of how you want to conceptualize it. So here, from here, the solution is identical to what happened before, but still, there you go. So what I'm seeing a lot in people's work is when they're asked to find the speeds of points on the object, that they are thinking of those points as independent things. And that is not the way to think of these problems. Think of the thing holistically. Our goal is to find our holistic quantities and then use our holistic quantities like omega and alpha to talk individually about what's happening at specific points. And so I hope this video helps you out with your understanding of these problems.